Yeah, Anand, please go ahead.
Yeah, so I forgot to hit the record thing, but okay, it'll just be 2 minutes delayed. Well, so for those who will be listening, just few quick announcements that we have made is 27 September is the deadline for first 3 experiments. We are canceling experiment number 8 and 9, so we'll have only 7 experiments, and the sub experiments within a given experiments, all parts are compulsory. Everybody has to try all those parts, and the grading will be accordingly. Okay. So also one thing came to my mind that should we have a WhatsApp group? I mean, it's going to be very difficult to manage, but is forum fine for people? I'm seeing a lot of people active on forum, which is very good. So maybe we can just continue with that, or you know, if it's more convenient for most people, then we can also start a WhatsApp group. So I mean, I'm not promising anything, but can we have some opinion as to how many people would like WhatsApp group, or you know, not like? So maybe first, for how many people will like WhatsApp group, maybe we can raise the hand. I can count.
Yeah, I think everybody would like a WhatsApp group because if you ask for it, yeah.
Okay, I get it. Okay,
there will be some Discord. Yeah, clearly. Yeah.
Yeah. So so how many people are happy with the current forum? So maybe you can lower the hand and raise it again. So you have to lower the hand and raise it again. Yeah, now raise it again as to how many people are fine with the current forum.
Okay, not too many.
Last 5 seconds. Okay. Fine, we get the idea.
Anand, may I suggest that rather than having a very large WhatsApp group, single, can we have our TAs, you know, monitoring one WhatsApp group? That might be easier.
Section wise.
And then we can be members of each of those.
Okay.
Other than, because one whole large might become just too large to manage in terms of attention.
Fine. So yeah, so we'll think about the suggestions. I mean, we're not promising WhatsApp group again here because it has its own set of complications, but we just wanted to have, you know, what people are thinking in terms of what they want.
Okay.
So until we have the WhatsApp, I think we'll communicate through forum. And only problem that I see with the forum is that somebody even replies, one doesn't get the notification. Otherwise, it's as good as probably WhatsApp, and maybe more organized than WhatsApp.
Sure. And the WhatsApp requires some discipline. No good mornings and happy birthdays and none of all that. It has to be purely lab-based stuff. Otherwise, it becomes unmanageable.
Yeah. Okay. So today's thing, there's 2 parts. One is this is regarding polarization optics. First one is the Malus Law, and second one is the kind of Rayleigh scattering. This is not covered in the theory part, but I think Harsha will present a brief introduction as to how to kind of understand it and see that the Rayleigh scattered light is polarized. But I will just do a very brief intro to Malus Law. So let me just share my. I think this everybody is familiar, so I don't think I have to spend more time here. Okay, so Malus Law, basically the question one asks is, suppose, well, what I have drawn here is just the XYZ plane, sorry, XYZ coordinate system. And let's say you have an electric field polarized along the X direction. And this is propagating, of course, along Z. And then at some distance, let's put a polarizer. Now let's say this polarizer is oriented, I mean the polarization axis is oriented along a direction which makes an angle theta with the x-axis. So this is the orientation of the polarizer. This means the light polarized along x-axis will get through the polarizer, and the other one doesn't make it through. So the question is, what is the intensity? Okay, first of all, what is the intensity of light right at this, oops, right here? So the intensity is, well, if I write the electric field here, it is, the electric field is essentially, we can have some E naught in the x direction. So the this is the electric field, and so the intensity is just, you can just take E square, E naught square, or this we can call I naught, mod square of the field in the x direction. So how do we find what is the intensity here? So that is the question, that after the polarizer, what is the intensity here? So in order to find the intensity, we have to find what is the first, the electric field. So what is the electric field here? Now, before we answer this question, we have to see which frame or which basis we are representing this electric field. So here we are representing the field in the XY coordinate frame, but since here the polarizer is oriented along this axis, it would make sense to represent the field in this basis. So what is that basis? So this is, of course, the direction in which the polarizer is kept. So this we can call X prime direction, and we can have a perpendicular to that, which is the Y prime direction. So since we want to find the intensity, we want to write the electric field here in this X prime, Y prime frame. So this electric field that we have, electric field is still the same, nothing has changed, but it's just that we are representing this electric field now in this X prime, Y prime frame. So what is the electric field in the X prime, Y prime frame? So it is what? E naught cosine theta in the X direction, and then minus E naught sine theta in the Y direction. So I just want to point out this and this. It's just the same field. It's just there, sorry, X prime and Y prime. So this field and that field is the same field. It's just that this is written in the XY coordinate system or XY basis. This is written in the X prime, Y prime. So now the intensity that will get through this polarizer is whatever is a light along this X prime direction, that much we know. So for counting the intensity, what matters is only this part of the field, and this part is either absorbed or reflected or something. So we want to count that. So intensity is here simply E naught cosine theta whole square. So we can call it I naught cosine square theta. So this intensity being I naught cosine square theta, this is essentially the Malus law after a polarizer. So we just want you to kind of check this experimentally, that you do obtain this, this expression. So for that, you have to set up a laser. For example, we can have a laser over there. With the polarization oriented along some direction, and that means it has to be a polarized light. And then after the polarized light, you will put a polarizer. And then we need to see that when we rotate the polarizer, that means we put the polarizer at different orientation, this is what the intensity expression is. Here you also can check that the intensity going in the Y direction, that will be, Y prime direction, that will be E naught sine square theta, E naught square sine square theta. And if you just add those two, E naught square sine square theta plus E naught square cosine square theta, that adds up to 1. So that just says the energy is conserved, intensity is conserved. But if you just put the polarizer and look for what the intensity is through X prime, that is I naught cosine square theta. So this is a very kind of simple experiment. So let me just show you again very quickly. This won't take much longer. So let me stop this and start share. Where am I? Now you will need to. So what was that somebody had said? How do I make it? How do I pin it for everybody? Spotlight video, I guess. Yeah. So is it pinned for everybody? That video of my.
Yes, sir. It's pinned.
Oh, excellent. So
Yes.
so this is a very simple experiment we are doing here. So this is my laser. I guess you can see it. So let me just turn this on. Okay, so this is my laser. You can probably see the spot on the screen. What I'm doing, I'll put this goggle. This is kind of polarized. I do have two polarizer, but I'm using for something. So since it is polarized, the laser is unpolarized. You know, the sum of the light, maybe about 50% makes it through the polarizer. So the light after this goggle, which is a polarizer, is actually polarized. So now if I put a polarizer and kind of see the spot. Yeah. Oh, it's too dark. What happened to the laser? This should be. This laser eats up the battery like anything. So that is okay. So that is slightly better. Okay. So that's the intensity. Now if I rotate the polarizer, so in this direction, in this orientation, the orientation, now we can, I guess. In this orientation, the polarization axis of this polarizer, that's my hand and my goggle, is pretty much the same. And hence you see the maximum light now. But if I start rotating, you see the intensity starts to decrease. And when it is about 90, it is actually very low. Ideally, it should be 0, but none of these are perfect polarizers. So that's why you see some intensity. So if I rotate it back, it is the maximum intensity that I can see. So, and this follows a cosine square theta dependence. So the experiment is that you set it up like this. Instead of my goggle, you can put this other polarizer here, but I'm keeping it for some other purpose. And then you need to be able to mount the second polarizer, this one, on some rotating wheel or something, or you need to rotate it in some way that you can actually make measurements of the angle. And then as a function of this angle, you need to show that the intensity there at the screen, that follows a cosine square theta dependence. So that is a very simple experiment. So let me just ask one question. Now what I have here is the first polarizer oriented at some, let's say, vertical direction. This one I'm putting in the horizontal so that nothing, you can probably hopefully see it. My battery is dying, I guess I need to. Yeah. Now the question is, this is a polarized light right here, and then this polarizer is at 90 degree, and so Malus law tells me I should get nothing, so I have the minimum there. Now, if I put a polarizer in between at 45 degree, what will happen? Well, this is the 0, the minimum. Now, if I put a polarizer at 45 degree, will this intensity increase or decrease? Can anybody make any guess?
Increase.
And why?
Because before there was no component along the transmission axis. Like if it was at minimum, there was no component along the transmission axis. But when you introduce the diagonal one, you get a component along the transmission axis.
Yeah, fantastic. So that's precisely the thing. So you can see if it doesn't look that much of an increase, do I? Okay. If I put AC, this is increase. Just I'm inserting and there's an increase. So now, so here essentially what we are doing, this is at 0 This one is at 90. And this one I introduced. So if 0, 90, the transmission is minimum, almost theoretically 0. But then I put a 45 degree, I do see something. And that is because, as just somebody said, there's now a projection available with 2 projections. Now there is some light. So it's no longer cosine square 90 degree, which is 0. Now it is cosine square 45 degree times cosine square 45 degree, which is half times half, 1/4. So instead of 0, it is 1/4. So what happens if I add, let's say, one polarizer here at 22.5 degree and one polarizer here at, let's say, what, 67.5? No, yeah, 67.5 degree. Will the intensity increase further or decrease further or remain the same? Anybody? So if I added one polarizer, so with 0 and 90 only, it was 0. Well, this should be taken as 0, cosine 90 is 0. If I add one polarizer at 45 degree, we see the intensity has increased, and then we are taking that as cosine square 45 times cosine square 45, which is 1/4. Now, if I add one more polarizer, I don't have it, but if I add one more polarizer at 22.5, here at 47.5, sorry, 67.5, will the transmitted intensity increase or decrease?
It will be more than the current value.
More than the current value, excellent. So what if I add a few more polarizer, like infinite number of polarizers in the, decreasing by tiny amount such that the first one is 0 and the last one is, 90 degree. And let's say we add n number of them such that the rotation is pi by 2n. So you can see if we just do that, the intensity here will be equal to the intensity here. Can somebody see it? From cosine square 90 degree, which is 0, with one polarizer, we got it cosine square 45 times cosine square 45. Okay. And that gives me 1/4. So if you add infinite number of polarizer, you can essentially rotate the polarization because the light that comes out of here will be 90 degree polarized to this. But if you add infinite number of polarizers, you can essentially rotate the polarizer without losing the intensity. So this is a simple kind of a consequence of the Malus law, but in quantum mechanics, this also has a slightly more celebrated name. This is called the non demolition measurement. So you're kind of or this is also called the quantum Zeno effect, that if you're making continuous measurement, the state, this is called the quantum Zeno effect, that if you're making continuous measurement, the state of the quantum system doesn't change while evolving. So, well, that was aside, that has nothing to do with this course, but for this course, we just need 2 polarizer, one here for making this light polarized, and the other one on some wheel where you can, make the measurement of the angle and then verify Malus law. So this is all for the Malus law. So now I will hand it, or if there is any question I can take here, otherwise we'll go to the next thing, which is Rayleigh scattering. Any question here?
Sir, I also wrote it in the chat. So isn't this the same as what rotators do? Rotators are those things which rotate the polarization. They are usually some optically active material like sugar solution.
Yes, yes. Also, you can have the wave plates doing very similar things. Yes, but this is wave plates can also rotate the polarization from some angle to some angle, and you can also see it this way. Yes, you can also see it this way.
Sir, but over there, those materials aren't able to generate polarized light from unpolarized light. But these polarizers are able to generate unpolarized light, generate polarized light from unpolarized light.
No. Here also, I mean, the first one is the first polarizer is making a polarized light. So once the polarized light is there, then only we are doing that experiment. So first it needs to be polarized in certain direction, and then you put the infinite number of polarizer to kind of rotate the polarization, or you can put a wave plate, or as you said, sugar solution and things like that. But the first, it needs to be a polarized light.
No, I think Anand, he was asking whether in the optically active materials, whether they can make it polarized. The answer is correct. They cannot make it polarized. It is that every polarization will be rotated appropriately.
Yes.
Yeah. So it continues to remain unpolarized.
Yeah. And to see that
And
to see that effect
clearly,
you have to have to see that effect clearly. You have to start with the polarized light, just like here as well.
Correct.
Okay. Thank you, sir.
Any other question on this Malus law? Okay, so Harsha, maybe you can. I'll share the. Now you can.
Yeah, I can probably. Yeah. All right. So I'm going to discuss the Rayleigh scattering very briefly. So what I'm going to do is I'm going to share my screen and actually take help of Wikipedia because I think that's reasonable. But I would suggest that you read this book by Hecht. I'm also sharing something which is non-mathematical, which I'll share in the thing. But the book by Hecht, optics book, which you are following for the rest of the course, you should look at the derivation of a dipole scattering, which is coming out of, is basically same as a Rayleigh scattering. So let me just share my screen and then okay. Yeah, I hope everybody can see. So I'm just going to Wikipedia and looking at Rayleigh scattering. So you see, Rayleigh scattering is essentially happens when the particle that is scattering the light is extremely tiny. So you have a notion of a length scale. The notion of the length scale in optical scattering is largely governed by the wavelength of the input light. So let's say lambda is the wavelength. Then one can look at a ratio, right? I hope you can see my screen here. One can look at a ratio x, which is basically the ratio between the radii, in this case r for the particle, and lambda. So r by lambda is this it's a parameter. It's a non-dimensional parameter, dimensionless parameter, which allows you to look at various regimes of scattering. So for example, when you look at a piece of glass or a prism or a glass slab, clearly R is much larger than lambda. This is where you see this normal refraction, reflection, and so on and so forth. As you make the size of the scatterer smaller and smaller, that is, you decrease your R such a way that this particular parameter becomes comparable. For example, you could have a parameter where x is of order 1, where that would mean that R and lambda are comparable. In that case, you come to a regime which is called basically Mie scattering. Okay, so Mie scattering is again well-known scattering. That's what happens. For example, the white clouds that you see where the particle size is large, you get Mie scattering in nature. And when this parameter becomes much smaller than 1, so it should be like 1/10. That's the kind of sizes for Rayleigh scattering to start appearing. So when you have some parameter which x is, which is much smaller than 1, in that case what you get is, this is the formula that you get for scattering. All right, you don't have to worry about the derivation per se, but basically it is telling you, let me just tell you what the parameters are. I is the scattered light. I naught was the input incident intensity on the particle, right? Theta is the scattering angle, right? So by scattering angle, what I mean is, I hope you can see me. Let me annotate. Yeah, so let me annotate and then I will draw. Somehow my draw is, yeah. So for example, this is my input direction, and this is where my particle is, I'm exaggerating. So you see that if my light travels straight, this is theta equal to 0. So any direction that it scatters off, this angle is what is called as theta, right? That's my scattering angle. So this is my input, and this other part is my output. So that's the way one looks at this angle theta. So clearly theta equals to pi will be the backscattered light, right? So that is how one thinks about it. Capital R is the distance between the scatterer and the observation point. So clearly the intensity falls like 1 over R square. Then it has got this very important, 1 over lambda to the power of 4 dependence. This is something that you should keep in mind, right? That's very, very important. This 1 over lambda to the power of 4 is what actually it becomes a very significant color dependent scattering that you see in Rayleigh, which is not seen in me scattering or any other system, any other scattering phenomena. That's kind of bright color distinction comes from this 1 over lambda to the power of 4. That would mean basically the following. Imagine, so 1 over lambda is same as, let's say, frequency, omega, right? So omega to the power of 4 implies that if omega was, twice as large, right? Then that would mean that my scattering is going to be 2 to the power of 4, right? That is the kind of 16 times more that light is going to be scattered in comparison to omega, which is smaller, right? So it is this lambda to the power of 4 is strong lambda dependence is the characteristic of Rayleigh scattering. Here n is the refractive index of that particular scatterer. It could be glass, it could be whatever, particle size, whatever. And d is the diameter again of the particle itself, right? So one can now actually integrate out one can look at the total amount of scattering. So one can integrate it out, integrate over all possible thetas, and what you get is something called Rayleigh scattering cross section. Again, the things to note here is basically this lambda to the power of 4 kind of lambda to the power of 4, 1 over lambda to the power of 4 dependence in whatever we see. Okay. Now, let me just tell you. So this is precisely what causes. So let me share another screen and just hang on a minute, and I will. Yes. Yeah. Oops. Can you see my screen?
Yes.
Yeah. So this is the kind of stuff that one is talking about here, right? So we have our laser light, and if it is polarized, then you see that the electric field sort of remains in a plane. That's what you call as plane polarized. In this case, the direction is x, so it is x polarized, right? This is what is a linearly polarized light or plane polarized light. I can come in at an angle. So let's say this is my screen XY, just like Anand showed you earlier, X and Y. So one can look at the electric field, which is oriented at angle theta. So there is a X component, there is a Y component, and you can have a situation where the light is randomly fluctuating and it is unpolarized, right? So this is precisely what is coming when you're looking at, for example, sunlight or a torch, for that matter, even our laser is largely unpolarized. So when you have unpolarized light, essentially what you have is you can think of equal components along any two axes, or any arbitrary axis will have equal intensity. That is, if I rotate a polarizer across unpolarized light,
Harsha,
right?
you could use a pointer.
Yeah. Let me just, sorry.
Yes.
Annotate, yes. So if I'm looking at unpolarized light, actually my pen is not working somehow.
Oh, okay.
So I'm using my finger. That's what is making it messy. Okay. So I have this unpolarized light, and irrespective of the direction in which I keep my polarizer and I rotate it, if I rotate it in whichever way I like, the intensity is not going to change because that's unpolarized. That's a characteristic of unpolarized light, right? Yeah. So now let me just get to the polarization dependence of Rayleigh scattering. I hope you can still see my screen.
Yes.
Yeah. So this picture is what I want you to keep in mind. So let us say I am, again, let me draw. So I'm coming in from this direction, right? This is the region, at the center is the region where I'm getting scattered. So clearly you see if the electric field is pointing vertical, it is going to generate, basically what you're looking at is a dipole scattering. That would mean that the particle size is so small that, the electric field separates out the positive and negative charges in that particle. The particle is, think of it as point particle. So you see that a single dipole is essentially what is being generated within this small particle. So the electric field basically separates out positive and negative charges, and because the electric field is oscillatory, it is going to oscillate the dipole along that particular direction. Similarly, there is going to be an oscillation along y, and for that matter, every other direction one can think of, there are oscillations that are being generated at the point where the light interacts with the particle. Now, when I'm looking at, as I look at the beam, as I'm looking into the beam, that is looking towards the source, I basically get all these contributions which are coming out from the dipole. And the dipoles are now oriented in random directions because my input light itself was driving the dipole in random directions, right? So this is a collection of independent dipoles. You can think of it like that. And you can think of this light as coming in. But imagine that you're now observing this same scattering medium in a direction which is perpendicular to the direction of propagation of light. Now, clearly you will see, okay, so this is another important thing. I don't know whether dipole scattering has been taught in the class yet, but let me just use this part of the, to show you a dipole scattering. So if let us say that this is my dipole, right, with the plus and minus, and this dipole is oscillating, then what happens is the following, right? The light which is emitted by the dipole is largely like a donut. It is in this plane, right? And it has got, so large amount of light is there in the plane perpendicular to the dipole, and the light is being emitted. There is very little light, right? Let me just draw that by green. There is no light in the polar directions, right? In the direction in which the dipole is oriented, the light is largely in the equatorial plane, and it has got this, theta dependence. Basically, you can, if the theta you're measuring from, if you're measuring the theta along the dipole, then it's a sine square theta dependence is what you get in terms of the intensity of a dipole. So you see that clearly when the light is coming towards me, and I'm watching this light in the perpendicular direction, you see that there are two components that one can break up the light with, right? One is the vertically upward component, and one is the horizontal component. Now, clearly the vertically upward component will give out light towards me, which is what I am observing here. So look at this observation, and you see that this is vertically upwards. The light, the dipoles which are in the horizontal plane, right, which are oscillating horizontally, I am looking at the poles of that, right? So there is no light which they can contribute towards my orthogonal direction. So clearly you see that the light which is scattered into my eye cannot be contributed by the dipoles which are oscillating in the horizontal plane. They are only coming from the dipoles which are oscillating in the vertical direction, right? So what I get is actually a polarized light in the orthogonal direction. And in between these two angles, one is the direct angle and this one is a 90 degrees scattering angle. Anywhere in between, you see it's partially polarized. So similarly, this diagram will tell you what is the orientation of light that you expect to see when you have something like the Rayleigh scattering. So I'm going to send you this particular book chapter, right, which is there to be shared. You can basically, I will put that up in the resources, right, and you can have a look at that. And you can read through this, also refer to Hecht for more details. And what I want to do now is quickly show you a demo in which you can actually measure this stuff, right? So I will stop share, and I want to probably switch on my camera. And
Sir, we can't hear you.
no, Anand, can you spotlight my camera?
Oh,
so that.
Or I'll make you the, where are you? Now I can. Okay. I'll make you host, then probably you'll have the.
Okay, fine.
Because I don't see that option on my side.
Okay, all right.
So now that you're host, you should have that option.
Advanced. Where do I see the spotlight business?
In just the participants thing, you click on
the participants. Yeah.
And then on the side there are a few options. So beside your name, there's a camera. There is more. There's a blue button. If you bring your cursor onto your name, there's something called more, and then if you hit on more, I think
on more, right? Yeah. Correct. So it says live on YouTube, live record this. It doesn't tell me
spotlight.
It doesn't tell me spotlight yet. So let me just.
So I think if you right click on your video, there should be a spotlight option.
Actually, right click on my video and it has shut me off. It should give me options, right?
No, sir. Where you see the video itself.
My video itself. Yeah. Oh, yeah. Spotlight for everyone. Oh, thank you so much. You guys are brilliant. Okay. Right. So I hope you can see this glass of water that I have tried to keep there. That is going to be my medium, right? And clearly I want something that will. All right. So what I have done is, this is a clear glass of water. I hope you can see that.
Yeah.
Right. And what I have done is, I have taken 2 drops of milk and I'm adding to it. All right. I hope you can see that. And I'm trying to make a scattering medium out of it. Hopefully now it looks nice and milky, right? Now what I'm doing next is opening my kit and removing my torch, right? Because that is a torch has got all the colors. Roughly, I mean, it's a white light, so it will have color and hopefully we'll be able to see. So this is the torch, which probably you can clearly see that the light is completely, it's white, right? Now what I'm doing is the following. I am, I hope I can do this if I take it far away. So actually I can see, I hope, can you see there is a bluish glow?
We saw a flash of blue, but it's white actually. It's probably saturating, I guess. But
no, I can see it here. Problem is I can see it here. Just handle this.
So maybe you could try reducing the beam intensity by covering it with your hand.
Or a piece of paper, I guess.
Hello. Yeah. Actually, it is just too much scattering. I should have.
Can you cover it with a
Actually,
piece of single sheet of paper, Harsha? Maybe
yeah. Let me just do that. Let me just do that. I think what I will do is make a small hole so that you do not see what you need to see. Right. And now let me see whether you can. Can you? No.
no.
White paper is again a bad idea.
No. Put the paper on the torch. On the,
No, actually.
that doesn't work.
No, that will make it too small. No. Okay. Let me see whether that works.
Now we see something.
I am able to see the blue, but my camera
bright.
is not catching it. That's the problem.
Yeah, it is still pretty bright.
It is, yeah. See, what is happening is the following.
I don't know. You put your hand and then we saw blue. Just put your hand in front of the torch to block the torch. Yeah, now we can see some blue.
No, okay. Let me just. I think.
Just block the half of light or most of light.
Yeah. I think 1 second. I will do this. Now I know what to do. Okay. Can you? Can you see now or no?
No.
No, I think I'll go back to my. Actually, it's you can actually see it directly with the eye, but it is not being seen in the camera. How about this? No.
Just put your hand on the torch. I think that reduces the intensity, and I think we saw a flash of blue with you when your hand was accidentally on. Yeah. Now we can see it.
Achha.
Yeah. It's a nice.
Yeah. Correct. Yeah. This is better. See, so and not just that, I mean, so let's say this is blue, and can you see now? Still, now I don't have enough hands to put the polarizer.
Or maybe you can put a few sheets of paper, and that will reduce the intensity.
From the torch, right?
From the torch. You just fold it in 4 times.
Not really. Actually, single layer itself is terrible.
Oh, this is too bright.
Too bright.
I just fold it, in layers.
Yeah. I think this is better.
Even this is too bright. Now we can see some blue. Yeah. Yes.
Actually, it's got to do with the narrowness of the beam. What I want to show you is the following: that you see that this the
polarizer.
The polarizer, see, completely cuts off. Can you see that in the orthogonal direction? Okay, so let's look at this light, and you see the polarizer, right? Can you see that?
Yes.
It is polarized. I'm rotating the polarizer. This is one orientation. Just hang on 1 second. It's a mess. I think showing it is a mess, but otherwise it's quite visible. You can see it at your homes.
Hello. 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 Can anybody hear me?
Yes, I think Professor Bhandre has disconnected.
Yeah, no, there's a power cut in the campus, so I think probably okay. I'm back on my data, so I think he probably is in the middle. So let's just wait for a minute or two for Harsha to show up. Okay, in the meanwhile, I just wanted to kind of point out there's a forum regarding.
Sorry about this.
Yeah, there's a power cut.
Power gone. Okay. Sorry, I don't know. Yeah. So again, let me spotlight. Does it work? No. Am I the host still?
Oh, hang on. Let me just try.
Anant, am I the host still?
Let me check. Yeah, you are the host now.
Okay. So, yes. Now, it has not done it. Okay. So my glass of water remains as it is. Okay, poor bandwidth, is it?
Yeah, I think your video is.
Yeah, my bandwidth also is. Okay, anyway, yes. So I believe you can actually look at this and you can test out that the scattered light is actually polarized. Okay, in the orthogonal direction, you can clearly see the change in the amount of light that will go through. Yeah, it's a messy business, but anyway.
Okay.
All right, so you can look at the scattering which is coming out of the sky, right? So if you point the polarizer upwards to the sky, right, away from the direction of the sun, orthogonal to the direction of the sun, you'll actually see that the light that is coming to you is polarized. And as you rotate, the sky will get darker. So one can actually make measurements and see at various points in the sky, one can make out how much, what is the degree of polarization that you would get. So the blue light that you get in the orthogonal direction from the sun, which is the Rayleigh scattering, that is why the sky is blue. And that is what makes the basically the light which is also polarized. So you can measure its polarization and look at the nice lambda dependence that you get. So this is, by the way, the same reason of which, for example, when you look at the evening setting sun, you see it to be orange because you're looking directly at the sun. The blue light, blue content has been scattered out of the, hence what you see is an orange or a reddish sun on sunset. Similarly, you see clouds which are white is because the particle sizes become larger. So what you have is a dominantly Mie scattering, not Rayleigh scattering. It is Rayleigh scattering that has this 1 over lambda to the power of 4 dependence, which is not there in Mie scattering. So because in Mie scattering, you're looking at larger particle size. There are multiple dipoles which are interplaying a role, which are playing, and the interplay between them is going to create different kind of a light, and hence the light is not, it doesn't have that lambda dependence, and also the polarization dependence is not as strong as in the Rayleigh scattering. All right, so if you have any questions, I will share. So the things you have to go through is the Hecht book on optics. Go through the Rayleigh scattering section, and also I will share this particular discussion on atmospheric scattering and so on and so forth. So please go through that. It is a non-mathematical description, and the formulas and all can be found on basically Wikipedia as well. But I think what we are looking for is the measurement of the amount of polarized light as a function of that angle, of the function of the scattering angle. Do it at 90 degrees, do it at a few other angles, and see the variation, or rather the variation, the partially polarized. You will see, when you put the polarizer in the front, that is along the input beam, you will see no variation at all. In comparison, you will see dips which are getting deeper and deeper as you come to the orthogonal orientation for measurement. So this is the kind of thing that you can explore and do it for a few angles, and that should be sufficient for the experiment. All right, any questions?
Any question on this one or the previous one?
I think we have probably apologies for this power cut and whatnot. And
okay.
all our connections went bad, and my video.
Yeah. So if there is no question, I just wanted to just one comment. There's a comment on the forum. This is regarding student returning back to the campus. So my request and our request is to not use this course platform for anything other than the course thing. So no discussion beyond what we do. There are several other platforms for these kind of things. And so you should not be using this platform for putting in anything like this. So that will be our request. So again, any other question? Any question on polarization or the scattering or the other Malus law? So I think Harsha's connection is not working. Okay, so if none, then I think we can stop here. And I'll write these few announcements in the announcement on the MOOC section as well. So, okay, so we will stop here. Bye-bye.